Hi, in this video lecture, I'm going to explain about scalable unmanned air vehicles, unmanned aerial vehicles, multi-hop networking via multi-agent reinforcement learning with large language models. So this article is published in this year, July 2026. Okay. Why do you need UAVs, UAV multi-hop network? So natural disasters such as earthquakes, floods, okay, etc., cause damage communication infrastructure. So all the terrestrial infrastructure, okay, may be damaged. So in 2024, United States experienced 27 disasters, each causing uh, one $1 billion in damage. Okay, total losses. Okay, so communication challenges. So base stations may fail, fiber optic backhaul links can be damaged. So large regions become communication dead zones. Rescue teams lose network connectivity. So victims cannot contact emergency responders. So the proposed solution is deploy a swarm of unmanned aerial vehicles, okay, that rapidly establish a temporary wireless network. Okay, support emergency communication until infrastructure is restored. See the problem statement: how can UAVs restore communication after disaster? So after a disaster, some base stations remain operational. So many user equipments are located in communication dead zones. So the distance between surviving base stations and users exceed the communication range of a single UAV. So multiple UAVs must cooperate to establish a multi-hop communication network. The research objective is to determine optimal UAV deployment to maximize user coverage, communication quality, and maintain network connectivity, adapt to dynamic user movement and changing network conditions. So what are the key challenges? So multi UAV coordination. Okay, each UAV's movements affects the connectivity of entire network. Dynamic environment, large search space. As scalability, number of UAVs increase, hundreds of possible UAV positions. Okay, numerous relay combinations, many possible network topologies. This is due to scalability as number of UAVs user equipments increase. Okay. So connectivity constraints. Each UAV must remain connected to neighboring UAVs or base stations to preserve end-to-end communication path. If you see this diagram, so there are two damaged base stations and one base station is operational. So in this scenario, the UAVs are deployed, okay, to form a network and serve the user equipments. Okay, to provide the communication services to the user equipments. So this is okay. In this disaster scenario. This is the role of UAVs to act as temporary base stations and provide communication services. So what is multi-agent reinforcement learning? So reinforcement learning, agents learn by interacting with an environment. So here they observe observe a state of the environment, take actions, receive reward, update policy, and repeat. So here the objective in any environment is to maximize the long-term cumulative reward. Okay. So instead of one agent is not enough. So we need multiple agents which are unmanned aerial vehicles. So why multi-agent reinforcement learning alone is not enough? So challenge one. So large state space as the number of UAVs increase due to scalability, states action spaces increases due to dimensionality. Challenge 2. Non-stationary environment. So during training, the environment observed by one UAV changes because other UAVs are also learning. Slow exploration. So basically, multi-agent RL relies on trial and error learning. Okay. For large UAV swarms, millions of interactions may be required. Many explode actions are inefficient. Training time increases significantly. So multi-agent RL alone is not enough. So we need large language models. So large language model is an AI model trained on massive amounts of text to learn reasoning, planning, decision making, and knowledge representation. So examples everybody knows these days GPT, DeepSeek. Okay, in traditional MARL, agents learn only from interaction with the environment, okay, requiring extensive exploration. So the proposed framework, so it's a high level architecture. So LLM guided multi-agent reinforcement learning, so with knowledge distillation and behavioral constraints for scalable multi-hop UAV networking. So you see the environment, you have base stations, UAVs, and user equipment. So information, each UAV shares local observations with others to obtain a global view. So the aggregated information includes UAV locations, link quality, user distribution, and data rate and network connectivity. So they aggregate information from other UAVs. So this can be done using graph neural network also. Next is LLM guided strategic planning. Okay, so LLM acts as teacher, the multi-agent RL acts as student. So here the LLM guided UAV positions should align with MA multi-agent RL UAV optimized UAV positions. So here we have prompting and chain of thought reasoning. So well-designed prompt, step-by-step reasoning chain of thought, understand users coverage gaps, okay, and relay propose strategic deployment. So the main goal here, main purpose of using LLMs is to deploy UAVs. So after the LLM output, okay, you need to verify based on some rules. The LLM output should be verified. Next is Hungarian bipartite matching. So Hungarian algorithm is used to match the one and also optimal one-to-one assignment between LLM target positions and MARL UAV agents. So whatever LLM suggested, it should match with MAR multi-agent RL UAV positions. So knowledge distillation, transfer LLM strategic knowledge to MARL agents. soft target guidance, cross entropy loss. Knowledge distillation means LLM access teacher, multi-agent oral access students. So whatever the knowledge from LLM should be transferred to the MARL. So there is a loss. It should not be directly cannot be transferred so over the time. So we define a loss, okay, that is called knowledge distillation loss. So this should be minimized, okay. So multi-agent student, so behavioral constraints, so guide relay UAVs. So UAV also acts as relays here, not only as base stations but also as relays to maintain strong links, okay, prevent disconnections, okay, improve network stability. So they will see the policy optimization. Policy optimization in reinforcement learning. Okay, we have weights here, beta 1, beta 2 are the weights of knowledge distillation and behavioral constraint. Next, decentralized UAV. So the training is centralized and execution is decentralized. So means each UAV makes action independently, executes actions independently based on its local policy. So this is the proposed multi-agent RL, okay, with language models. So let's see the problem formulation. So we model the multi-UAV networking problem as partial observable stochastic games, okay, where multiple UAVs cooperate to maximize long-term network performance. Or network performance is a reward. So stochastic games, okay, agents, multiple UAVs acting as independent decision makers. Okay, next is state, global network state. Okay, UAVs, user equipments, base stations. Okay, this is the state. What is observation? The local information observed by UAV. So UAV movement or deployment decision is an action. So network performance, coverage, connectivity, okay, data rates is the reward. Policy maps observations to actions. So each UAV selects an action based on its local observation. So what is the environment transition? So after taking an action, the environment, okay, will change from state ST to ST plus 1. So stochastic game framework. Okay, so this is the global state, global environment with all base stations, UAVs, user equipments, wireless links. So each UAV has a policy. Based on its policy, it executes an action. Take up observation. Okay. So after taking actions, the state will be transitioned to next state ST plus 1 on reward RT. So let's see what is information aggregation. So each UAV shares its local observations with other UAVs to obtain a global view of the network. So what is information aggregation? So individual UAVs have partial and localized information. It is by exchanging their observations with neighboring UAVs, they aggregate the information, okay, to form a global network view, so which improves decision making. So whatever the information, okay, so link quality, okay, this is one observation. So they should share. So this includes signal to noise ratio, user distribution, data rates, UAV locations, position, okay, network connectivity. So what is agent grouping? So UAVs are partitioned into groups based on their proximity, Euclidean distance here, where proximity is calculated based on Euclidean distance and connectivity to enable scalable and efficient coordination. So what is agent grouping? Agent grouping partitions UAV network into clusters, groups or clusters. So UAVs within the same group are closely connected and cooperate more frequently, while communicating between groups is limited to group leader. So proximity, okay. So this is agent grouping. So this also clustering is also used in wireless sensor networks. This is a old technique, not new. See reward decomposition. The overall team reward is decomposed into interpretable components. Okay. So let's see what is the overall team reward. So it is okay. So team reward RT, okay, plus connection reward and also relay reward. So it is a weighted combination, okay, of overall team reward and its combination. Uh, so here you can see connection between UAV and user equipment, and next is relay each UAV acts as a relay, not only as a base station, okay, but also as relay. So next, see the behavioral constraints. So why do we need this? So directly, okay, to prevent disconnection and cascading failures. Okay, select the base station, okay, with highest signal to noise ratio. Okay, if all SNRs are below threshold, okay, guide UAV towards, okay, base station with highest signal to noise ratio. Next is compute the normalized direction from UAVU towards the best base station. After calculating G star, so which is signal to noise ratio, next is desired direction. So desired direction, okay, direction also should be optimized. Okay, G star is the, okay, base station with signal to noise ratio minus, this is the L is the position of UAV. Okay, so directional guidance vector. Next is action mapping. So map each discrete action into direction vector. So you can see it has total 1, 2, 3, 4, 5, 6, 7, 8. We have 8 directions. So each action space, okay, the set of direction vectors. So find the action whose direction is closest to the guidance. Okay. Next, behavioral constraints. So include a loss when all SNRs are, okay, below the threshold. Okay, here you can see we are guiding UAV in a particular desired direction. Okay, that has highest signal to noise ratio. Okay, because this base station is still operational. So due to disaster, only a few base stations are destroyed. Not all. We are assuming that some one or two base stations may be operational. Rule-based verifications. The L checks the feasible LLM generated deployment strategies. LLM generated output, which is a UAV deployment strategies. Okay, they we should check the feasibility of it before they are used for knowledge distillation or transfer, knowledge transfer. So ensure that output generated by LLM, large language model, is possible and will not compromise the network connectivity, okay, overall performance. So this is called rule-based verification of LLM output. So in this scenario, UAV deployment strategies is the LLM generated output. So LLM output proposes a UAV deployment, okay, strategy, positions and group roles. Next is rule-based verification. The proposed strategy is checked against a set of predefined rules to ensure it is feasible. Okay. Verification outcome. Feasible strategy is accepted for distillation. So whatever infeasible strategy is rejected and not used. So before giving to knowledge distillation. Okay. So next step, only verified strategies are used for knowledge. What do you mean by knowledge distillation? So LLM access teacher and transfers the knowledge to multi-agent RL. So let's what is prompt engineering. So cannot directly LLMs cannot directly interpret thousands of numerical coordinates and network parameters. So a structured prompt converts UAV networking problem into a structured textual description that the LLM can understand and reason about. So you can see the prompt component, scenario description, task objective, output constraints. Okay, few short examples, provide some input, example input output pairs, current environment state. Okay, what is the current state of the environment, include base station locations and user equipment distribution. Okay, so this prompting engineering gives the best deployment strategies. So especially chain of thought technique. Okay, how does the LLM generate a UAV deployment strategy? Enables LLM to solve a complex UAV deployment problem through step-by-step reasoning instead of making a single direct prediction. So why use COT, chain of thought? Breaks a complex problem into logical steps, produce more reliable deployment strategies, provide high level guidance for MARL training. So we are using LLMs to guide, to assist the multi-agent deep reinforcement learning training. Why? Scalability. Scalability increases number of UAVs. In this paper, the authors uh, in the experiment, they used 150 user equipments and approximately 18 UAVs. So scalability is high. So reasoning process, user equipment distribution, so distribution of user equipments, base station locations which are not still operational, other than okay base stations which are destroyed, communication constraints. So in step one, the step one, chain of thought prompting technique, analyze user distribution. Step two, evaluate connectivity gaps. Step three, generate UAV deployment strategy. So output is candidate UAV deployment. So we need, what is the output? We need UAV deployment, means best UAV positions in the disaster scenario. So input, this is the input, this is the output. So knowledge distillation. So how does the multi-agent RL learn from the LLM? LLM, the relation is teacher-student. LLM acts as teacher, multi-agent RL as student. LLM first generates high-level UAV deployment strategy using chain of thought reasoning. This strategy is then transferred to the MRL agent to improve its learning process. You can see the flow diagram. LLM access teacher and it gives the deployment strategy. and we need Hungarian matching. Hungarian matching is to align the LLM outputs with MARL, okay, outputs. Okay, so matches the LLM deployment with corresponding, okay, UAVs. See the algorithm. This algorithm in the paper, okay. Let's initialize all policy networks, okay. Pi theta is the weights of the neural network. Pi is the policy. Proximal policy optimization is a RL algorithm. Replay buffer G catchy. So initial LLM memory, okay, is equal to final. So parameters number of episodes, episode horizon, T K training epochs, Q updates, LLM guidance interval, okay, QLLM. So episode for episodes, okay, 1 to n AP, reset the environment in the beginning, okay, initialize agent grouping for the episode. So in the first step, observation, okay, observation. So when partial observable environments, observation is different from state. So observe the environment. So get the environment, okay. Each UAV, okay, gets the local information. This observed information will be aggregated, okay, because these UAVs must share, okay. Next is how this will happen for each episode have time steps. Each episode has time steps like 50 or 200 time steps. Episodes can be 1000, 2000, 3000. So okay, periodic LLM guidance, okay. Next, MRL action selection. So observation is converted into actions using policy pi, okay, subscript theta, okay. Each UAV selects an action, okay. Next, transition. When when an RL agent takes an action, the environment will be transitioned into new state S, okay, subscript T plus 1, okay. So when takes an action, okay, it gets a reward, is a reward, okay, reward matching algorithm. What is Hungarian matching, okay. Okay, LLM targets and UAV agent should match, okay. There should be optimal one-to-one assignment between UAVs, MARL UAVs and LLM targets. So whatever LLM suggested, the deployment strategy, which is UAV position, should match the MARL, okay, MARL UAV positions. Next is reward decomposition. This already we discussed in the previous slide. Storage experience, observations, actions, reward, next observation, and this sigma star is the Hungarian matching parameter. Okay, PPO proximal policy optimization for pay box. Okay, it should be repeated. Let's see the setup. Like I said, 3.5 into 3.5 square kilometers is the disaster scenario, okay, affected area. Next is user equipment. Means ground terminals or which are mobile, which can be mobile users, laptops, 150. So relays 18. UAV acts as relays. Okay, base stations. Okay, 2. So disaster area. Okay, the baseline algorithms. Okay, these GVs. This is the paper I worked. Okay, and submitted to scientific reports. So this is also my baseline reference algorithm. Okay, these are the baseline. Baseline means state of the art. We propose the algorithm and compare against these baselines. So this is how the output looks like. So the only training curves. So x-axis number of training steps, okay, 10 million. Y-axis team reward, okay, average reward, okay. So this colored, okay, curves is the average reward, and this is the shaded regions is standard deviation, include the variation across multiple seats or training runs, okay. So narrower shading means more stable. You can see ours means proposed by authors, okay, is outperformed, okay, the baselines. Ours is the proposed by the authors, and it has outperformed the baselines. So what are the key innovations? Agent grouping task, okay, okay. Next is reward decomposition. So there is one key innovations, behavioral constraints, LLM based knowledge distillation. Okay, these are the key innovations of this paper.